In our last lesson, we discussed one-to-one and onto functions. We also defined that if a function is both one-to-one and onto, then it is bijective. For today's lesson, we're going to be discussing inverse functions. And before we get into the theory and the set theoretic notions of how we interpret inverse functions, I want us to go back to questions we have already seen before. In algebra and calculus, you have seen a question like the one that's in front of us. Let f of x be the function x plus 2 over x minus 3. Find the inverse function of f of x. So what I am going to do before we even get into the set theoretic notions is solve this as we usually would back in algebra and calculus, and then use this example to segue into how we are going to be constructing everything set theoretically. So let's go ahead and get started. So whenever we saw a question like this in the past, what we would do is interpret this as y equals, and then we interchange the x and the y's. So we go ahead and interchange the x and y's, and then we are solving for y. And this will give us the expression for the inverse function. So let's go ahead and do that. So if we interchange the x and y's, we will have x is equal to y plus 2 over y minus 3. We go ahead, multiply by y minus 3 to both sides. We have x times y minus 3 equals y plus 2. And now this here gives us xy minus 3x equals y plus 2. But we want to solve for y. So let's go ahead, bring everything that has y's to the left-hand side and everything that has x to the right-hand side. And that will give us, we have xy minus y, but I'm going to go ahead and factor out the y. So we have x minus 1. That 1 is coming from this y being subtracted. And then we have 3x plus 2. And now finally, we go ahead, divide by x minus 1. And now we have y equals 3x plus 2 over x minus 1. And now what we get from our work in algebra and calculus, we will conclude then that f inverse of x is equal to 3x plus 2 over x minus 1. So that's how this ties in with what we have done in previous courses. But how does this tie in with the set theoretic notions? So first off, in this work, we have not identified what the domain and codomain are. Like what is the input and the set of outputs? Because that's crucial when we are talking about something being onto. Specifically, we need to make sure that the range is equal to the set of outputs for that function. So let's first look at f. So in the case of f, actually I'm going to change to purple, and now this here will just be the transition to the set theoretic notions. So first off, if we want to define f as a function in this course, then we'll say let f go from the real numbers, but not quite just the real numbers, because we cannot plug in 3 into here. Because if we plug in 3, we of course are dividing by 0. Can't have that. So we're going to remove 3. And then we're going to go over to the set of real numbers. Now it turns out that this function is going to be one-to-one, but it's not going to be onto the real numbers. And the reason is that we will not have a corresponding output for 1. And so we can see that if we solve this equal here, where this is equal to 1, there is no value. So I'm going to go ahead and I'm jumping ahead, and now just so be defined by f of x is equal to x plus 2 over x minus 3. And now what I was just mentioning just a moment ago is that this function is not onto. So note that this function is not onto, and technically onto the real numbers. When I say onto, it's implicitly understood that it's the the codomain or the set of outputs appearing in this portion of the function. And so it's not onto the real numbers. And the reason is that if we go ahead and solve x plus 2 over x minus 3 and set this equal to 1, what we end up getting is that this becomes x plus 2, and then this becomes this equal to x minus 3. And now what we end up having is that the x's are cancelled. So we have the x's go away, and we're left with 2 is equal to negative 3, and that of course is problematic. So we can't solve for x. If this was equal to 1, we will have a problem. So 1 is not in the set of outputs. So 1 is not in the range of f. And so we got this, and so consequently, the range of f cannot be equal to the set of real numbers since we are missing 1. And so that's one way of viewing it in this case for the function. However, now I'm going to go ahead and name this original function f hat. And now, however, if we define f from the real numbers minus 3 to the real numbers minus 1, defined by the same thing, f of x equals x plus 2 over x minus 3 is bijective. And so these are some of the notions that we skimmed over when we first covered these sort of questions in the past, is that we were not thinking about this notion of bijective. And so we always talked about these functions, but the domain was something that we can compute in our own time, or if the question asked us to do it. But now, if we want to talk about a bijective function, we do need to know what is a set of inputs. And in this case, I'm removing 1, since what it turns out is that we can find every value. The outputs correspond to every real number, but 1. So we got this. And so, of course, I'm saying that this is bijective, but we haven't proven it. And then if we look at the inverse function, I'm going to define this by g. So let g be the function where we go from the real numbers minus 1 over to the real numbers minus 3, defined, and here I'm taking what I called f inverse in the past, by g of x is equal to 3x plus 2 over x minus 1. So that's this here. Now what I am going to do is compute f of g of x and g of f of x. So if we do f of g of x, we end up getting the following. So we have g of x is 3x plus 2 over x minus 1, so we're going to be plugging that into our function f of x. So it's going to be this plus 2, and then this minus 3. And so we get. And so here it is. Now we go ahead and simplify so that we have a common denominator. So we want to introduce an x minus 1 into the 3. So we're going to multiply by x minus 1 over x minus 1. And then similarly, we're going to multiply 2 by x minus 1 over x minus 1. So we're just multiplying by 1 cleverly so that we can continue to simplify this expression. And that gives us this here. And then upon simplifying the algebra, we go about getting 5x over x minus 1 over 5 over x minus 1, but then that simplifies to just x. And if we do the same thing for g of f of x, so now we're going to go ahead, plug in f of x, x plus 2 over x minus 3, into every occurrence of x inside g of x, that will give us the following. And now if we go through and simplify the algebra for this expression, we get. And so we get this expression, which we then can simplify and continue to simplify to get 5x over x minus 3 over 5 over x minus 3, and that simplifies again to x. And so in both cases we get x. But now in the language of functions and relations, we can interpret this fact being x as the identity relation, that is, those ordered pairs x comma x. And so let's go ahead and make this precise, because here we have our function g, and we have shown that upon taking these compositions, we get back x. One of the things that we will do today is that if we have that both f of g of x and g of f of x giving us back x, that will allow us to conclude that both f and g are bijective. So today's lesson will imply that f of g of x being equal to x and g of f of x equal to x. Since both of these are equal, this will imply that f and g are bijective, and f is equal to g inverse, and g is equal to f inverse. And so that's one of the goals for today. The benefit of doing this is that now we don't have to verify that f is 1 to 1 and onto. If we get this equality here, that this is equal to x, that would suffice to conclude that we do have a bijective function and what their corresponding inverse is. So now let us continue, but what we are going to do is redefine f and g in the notation that we have been covering so that everything is done set theoretically. So we have that f is a relation, and so f is the relation where we have its ordered pairs x comma x plus 2 over x minus 3 until now this is an element in the Cartesian product of r minus 3 cross r minus 1. And so of course here x is now in the real numbers minus 3. And so that's our function f. We have our g, and g is x comma, but now 3x plus 2 over x minus 1, and now this is in the Cartesian product, r minus 1 cross r minus 3. And so now we have that x is now an element in the real numbers minus 1. So x is not equal to 1. And so that's the first difference, is that now f and g, if we talk about them set theoretically, this is what we are looking at. This is a subset of a Cartesian product. And f inverse, of course, by f is a relation. Well, it's a function, but it is a relation. And so we know that f inverse is just flipping the coordinate. So this is x plus 2 over x minus 3, comma x. But when we look at f inverse, we're flipping the elements in the ordered pair, so the Cartesian product is also going to flip. So now we have real numbers minus 1, Cartesian product, real numbers minus 3. Such that x is in the real numbers minus 1. Actually, minus 3, since we're corresponding to this x here. And so that's how f inverse will look like, just from our definition of what it means to have an inverse relation. We just flip the ordered pair, and now we have our definition. But it turns out that this expression here is exactly the one that we have for g, as we have seen. But now, before we continue, let us now look at the following. We did do the composition of f and g, and we got that those gave us back x's. So how are we interpreting these? Well, we can visualize these two functions, f and g, in the following way. And so here's our visualization. So f has domain, real numbers minus 3, outputs real numbers minus 1. And then we have g, who has domain, real numbers minus 1, and then outputs real numbers minus 3. When we take the composition, we are really taking essentially this arrow. So we're going from here to here, and we have g composed f. And so just the way we interpret this, we do f first, then g. And so that's our composition. And then similarly, when we look at the bottom portion, we have real numbers minus 1, domain of g. So we go via g to the real numbers minus 3. And then we have f as a function whose domain is real numbers minus 3, outputs real numbers minus 1. So that gives us, on the bottom, we have this arrow now going from real numbers minus 1 to real numbers minus 1, where now we do f composed g. And so that's the composition. But what does it mean that we're getting back x for both of these? Well, that's the identity relation, but the identity relation on the domain. So what we have by what we just did earlier is that this here is telling us that g compose f is equal to the identity relation on the real numbers minus 3. And recall that the way that we define the identity relation on a set A is as the set of ordered pairs x comma x in the Cartesian product of R, of the set given. So in this case, R minus 3, and so we're looking at just this set here. So x comma x is in this Cartesian product, and similarly, f composed g is also an identity relation, but now the identity relation on the real numbers minus 1. And so now this is x comma x in the real numbers minus 1, that Cartesian product, the Cartesian product of that set with itself, so r minus 1 quantity squared. And so we got this here. And so one of the things that we will be investigating today is considering what happens when we have compositions that are equal to the identity relation on the given domain of that composition. And one of the things that we will prove is this thing that I mentioned just now, that if we prove that f composed g is equal to the identity relation, and so is g composed f on the respective identity relation on the respective domains, then that will imply to us that both f and g are bijective. Because as of right now, the example that we have done, I have not shown that it is one-to-one nor onto. But the benefit is, because we have this g and we have the compositions give us back the identity relation, that would suffice to deduce that the functions are in fact both bijective. So let's go ahead and get started with some results to get towards that proof. So the first result we are going to prove is the following. So f is a function from a to b, and if the function is bijective, that is, it is both one-to-one and onto, then the inverse relation f inverse is itself a function from b to a. So let's discuss the intuition for why this is true. Well, set theoretically, the function f is a subset of a cross b. And f inverse is a relation on b cross a. So whenever we have a relation, we have an inverse, corresponding inverse relation. And the property is that if we have x comma y is in f, then that will tell us that y comma x is in the inverse relation. But if we want to prove that the inverse relation is itself a function, what we really need to do is that this is defined for every element in B. So let's go ahead and discuss what we need to do to show that it's a function. To show that f inverse is a function, we need to show the following. So the first thing is, for every element in the domain of f inverse, so namely B, so for all B, in B, we have that f inverse of B is defined. So that means that every input in B has an output. Every element of B has an output under F. So that's the first thing. The second thing, and I'm going to scroll down to the bottom, is that we need to show that each input has exactly one output. Each B and B has exactly one output in A. And so we have exactly one output in A. So let's go through the scratch work for how we would prove this. So the first statement we need to prove is that for every B in the set B, f inverse of B is defined. Well, this one is given by the fact that f is onto. Since f is onto, we have that for each B in B, there exists an A in the set A such that A comma B is an F. That is, f of A is equal to B. So we got this, but A comma B being an F, that means that B comma A is in the inverse relation. So in particular, B comma A is an F inverse. And now that tells us that every input in B has an output. Under F inverse. Granted, that doesn't tell us that this is a function, because now we just have that every input has at least one output, but it may have multiple, in which case it will fail to be a function. So now we need to show that it has exactly one output. So notice that right now we use the fact that it was onto. Now we're going to use the fact that it is one-to-one to prove that it has exactly one output. So here's how we're going to do this. So if we had that there was more than one output for some B, so we will have the following. So suppose that B comma A, actually I'm going to switch it to B comma X, and B comma Y are in F inverse. If we have the B comma X and B comma Y are in F inverse, that tells us that X comma B and Y comma B are in F. So we have X comma B and Y comma B are in F. But then we have f of X is equal to B, which is equal to f of Y, and the fact that f is one-to-one tells us that X is equal to Y. And that tells us that now the X and the Y are both the same, so we have, for every input, there is exactly one output when we translate that back, since X and Y are the same. And that finishes it off. And so that's the sketch for Theorem 531. So now let's go ahead and formally write this up. So here's the formal proof. So we have f is a function that is bijective going from A to B. So the first part that we had in our scratch work was to show that every if we look at the inverse relation f inverse, every input has an output, and we use the fact that f was onto for that purpose. So let b in, so let's go ahead and switch to y's. So let y be in b. Since f is onto, there is an x in a such that f of x is equal to y. In particular, y comma x is in the inverse relation. So we have y comma x is in f inverse. And so consequently, each y in B has a corresponding x in A such that y comma x is an f inverse. So this is telling us that every input has an output. Every input of B has an output. So now we need to show that this is, so this tells us that portion. So now we need to show that that f inverse is a function. So we need to show that that output is unique. So it remains to show that each y in B has exactly one output, x in A. So to this end, suppose y comma x and y comma z are both in the inverse relation. Then by definition, we have that x comma y and z comma y are both in F. In particular, we have that f of x, which is equal to y, is also equal to f of z. Since f is 1 to 1, we deduce that x is equal to y, which shows that f inverse is a function. So now we can upgrade it to this notation, is a function. Now a comment on Bellemant's writing style. So in Bellemant's text, he would simply finish the proof by saying, which shows that f inverse from B to A, and this notation, from it is inferred that this is a function. Commonly, that is not a common usage, so usually we would just go ahead and just write the whole phrase, f inverse is a function. But for the purposes of this course, this is fine, but just be mindful for future courses, you may want to say that that is a function. So from our previous result, now we know that if we have a function that is bijective, then its inverse is also a function. Now for the next question, we're going to do something similar. So we're going to suppose we have a function from A to B, and we're going to call that function f. And now we're going to assume that the inverse relation is a function from B to A. And what we want to prove is that f inverse compose f is equal to the identity relation on A, and f compose f inverse is equal to the identity relation on B. So once again, the I sub A, this is the identity relation. So this is the collection of ordered pairs x comma x such that x is in A, and I sub B is the identity relation x comma x such that x is in B. So that's what this notation means. And the proof of this is now automatic. And what I mean by automatic is that we can do it just by following the definitions. Because if we go ahead and so let's go ahead and show this portion here first. So that f from A to B and its inverse relation, B functions. Now we're going to take an arbitrary x and A, then f of x is equal to some y in B. Now, this tells us x comma y is an f, and thus f inverse contains y comma x. In particular, we have that f inverse composed f evaluated at x is equal to f inverse of f of x, which is now y, which is now, by this here, tells us that if we have y as an input, we have x as an output. This is equal to x. And so we got this here. And so now that establishes that this is I sub A. So, thus, f inverse compose f is equal to the identity relation on A. And I'm not going to do the second part, but that's a similar argument. It shows that f compose f inverse is equal to the identity relation on B. And so we're done. So one thing that we are using implicitly in this proof is the fact that f and f inverse are assumed to be functions. Because that is telling us that this x, that input x has a unique output y. And because f inverse is a function, the input y has a unique output x. And that's what allows us to say that we do have, that this composition gives us back x. And since x was arbitrary, this tells us that the identity relation, the composition is equal to the identity relation. But now, to emphasize what I'm saying out loud, by definition of f inverse compose f, this is the set of tuples x comma z in the Cartesian product of A with A, such that there exists a y in B, such that we had f of x is equal to y, or how we used to write it in the notation of relations, x comma y is in B, in f, and y comma x is in f inverse. But since each input has a unique output, y, when f is a function, that forces this existent to be there's only exactly one choice of y. And so in this case, we're going to have exactly x comma x. And so that finishes it off for Theorem 532.